In our previous video, we talked about what it means to be an absolute max or min, and also what it means to be a local max or min. So one of the things we discovered in our picture was that many local minimums and maximums are achieved at peaks of what I call a mountaintop and valleys between the mountains on our curves. And when that occurs, we saw that we had a horizontal tangent line at many, but not all of the extreme values. So one of the ways we're going to look for a local extreme value, sometimes called local extrema, is to take your derivative, the slope of your tangent line, remember that's what same thing, and set it equal to 0. So we're looking for, on the curve, we're looking for those points where you have a horizontal tangent line. And those are going to be local mins and maxes. Now, there's a note here. This helps you find many of the local extrema, but it's not sufficient to find all of the local extrema. So if you recall in our picture, we also had one where it didn't have a horizontal tangent line because it had a cusp. So it looks something like this. So it came in a nice smooth curve and then it did this weird dippy thing. This point here, f prime, is not equal to 0. This is another one that we have to consider, and that's listed here. So number 1, find all the places where the derivative is 0. That's the first derivative theorem for local extreme values. Second, the other interesting points are going to be where the first derivative is undefined. So this cusp here, that's what we call this, is one point where the derivative is undefined. Another point that we need to consider is if there are endpoints. If it's a closed interval that we're considering, you need to consider your endpoints of your function. They may be local or absolute extrema. So those are the 3 places we're going to look to find our extreme values. Now, if you find these points, we have a definition for them. Any interior point, so we're not looking at the endpoints, not case 3, case 1 and 2. Any interior point of the domain of a function f where the derivative is 0 or undefined is called a critical point. So if you find 1 and 2, we have special names. These are called critical points. So you're going to look for all the critical points where the derivative is 0 or undefined. And then if you have a closed interval, you're also going to look at the endpoints to look at extrema. Note, being a critical point does not mean that there is an extreme value at that point. So we're going to look for everywhere that the derivative is 0 or undefined, but not all of them will be extreme values. These are where they can happen, okay? But they don't necessarily have to be an extreme value. We're going to look at a method for testing each of the critical points to determine if it is in fact a local extreme value. So find all your critical points, and then you're going to test them to make sure or discover if they are extreme values or not. For now, we're going to focus on finding the absolute extreme values. All right, so finding absolute extreme values, or absolute extrema, on a continuous function f on a finite closed interval. So this is our topic for this video. Another video will focus in on the local extrema, but they're found in a similar way, partially. Number 1, find all critical points of f. So remember, critical points is saying find your derivative, find where your derivative equals 0 or undefined. So find all of those points. Number 2, evaluate your function f at all critical points and the endpoints. So you're going to take your f of x, and you're going to take every single x value you got from this list, from number 1, and also your endpoints. You're going to plug each of them into your function. Take the largest and smallest of these values. That's all you're doing. You're finding all the extreme values, and then you're looking for which one's the biggest and which one's the smallest. So let's try an example. Find the absolute max and min values of the following function on the given interval. Notice this is a closed interval. We include the endpoints. So we're going to first find the critical points, and then we're going to plug in our endpoints to discover where the absolute min and absolute max is. All right, so what is the derivative here? Remember, when we look for critical points, we're looking for where the derivative equals 0 or is undefined. Okay, so what's the derivative of this function? Well, this is actually a linear function. This is actually a straight line, which you can actually use that information to help you. Think about a straight line. Where's the max and the min going to be? Okay, I'll let you think about that while we work it out. So the derivative of this, let's see, 2/3 hangs out. The x, well, that goes to 1, and the 5 disappears. So this is our derivative. So it says we need to find out where this is 0. Well, the derivative is 2/3. When is it 2/3? No matter what x I plug in, the derivative will always equal 2/3. So this will never be 0. This will always never be undefined. That's impossible. It's defined to be 2/3 no matter what you plug in. So in this case, there actually are no critical points. Well, that's interesting, but it makes sense because we're dealing with a straight line. Now this is a positive slope, so we're dealing with a straight line that looks something like this. We start and we end. Okay? So how are we going to determine our extreme values? Well, we have no critical points. The only other thing we need to test is the endpoints. If you understand what your function is doing, you understand it's an increasing function, then you can already answer that question. But let's follow the steps. Step number 2 is to evaluate your function at your critical points, there aren't any, and your endpoints. So our endpoints are -3 and +3. Let's plug those in. So f of -3 and f of +3. All right, so 2/3 times -3 plus 5. So let's see, the 3's cancel, and we get -2 plus 5, or 3. If we plug in 3, we have 2/3 times 3 plus 5. The 3's cancel, so we have 2 plus 5, or 7. So what did we find out now? We're on step number 3. The largest value is your absolute max, and your smallest value is your absolute min. Now this makes sense because your function was increasing, straight line, so it would start our interval at x equals -3, and it would end at x equals +3. A straight line connecting these 2 points in an increasing manner, you can already say that this is going to be your absolute min and your absolute max. Now the x value is not the minimum value, the x value is not the maximum value. But the x value tells you where those happen. So to find your min and your max, you do have to plug it into the function and find out what the y value is. The y value is the maximum value achieved and the minimum value achieved. All right, let me bring up another one. Find the absolute max and min for the following function. Now this one's not a straight line. This one's actually a parabola. So if you know a parabola and you understand a parabola, you can work with that. But I want to show you how to follow the steps. So step number 1, if you recall, is to find the critical points. So how do we find critical points? So f prime equals 0 or undefined. You're going to find undefined very rarely occurs in our problems, but always write it down to help you remember that you need to make sure you don't forget about that case. Because if you forget about it that one time when it actually matters, well, you might get the wrong answer. All right, so to do this, we need to find the derivative. So our function is up there at the top. The 4 goes to 0, that's gone. But negative x squared, take the derivative, we get -2x. So the question is, when will this equal 0 and when is it undefined? Well, undefined is fairly straightforward for us. Undefined is going to occur when we have x in the denominator. So we're going to focus on when the denominator equals 0. Well, that can't happen here because we have no denominator. This is going to be defined no matter what x you plug in. Undefined can also occur when you have roots because your domain can be limited, and logarithms because your domain can be limited, but those are ones that I did not see in our work. So things that you should keep in mind, but we're not going to focus on those in our course. Solve for x. So we're going to divide both sides by -2. And the answer is, at x equals 0, f is equal to 0, or f prime is equal to 0. So this is going to be our critical point. We found one critical point. We also have the endpoints, -3 and 5, and they're included. This is a closed endpoint, or closed interval, so we include both of those endpoints. So step 1, find all the critical points. Step 2, evaluate. So take your function, plug in your critical point, and your endpoints. So -3 and 5. Critical point, endpoints, find out what you get. All right, so if we plug 0 in, so 0 squared minus 4, that's -4. -3, but we have a negative outside of our square. So that's +9, -9, minus 4 would be -13. Plug in 5, we have -5 squared minus 4. So that'd be -25 minus 4 or -29. So now that you've plugged everything in, step 3, the largest value is your absolute max. The smallest value is your absolute min. It's a little tricky here for some students, so make sure you're careful in your answers. Which one is your absolute max? -4. It's your absolute max. So your absolute max is -4, and it's achieved at x equals 0, your critical point. Your absolute min would be, well, the other two then. Well, the smallest value we have is -29. Remember, these are negative numbers, so the bigger the negative number, the smaller it is. So this is our absolute min, and it occurs at the x value of 5, one of our endpoints. All right, so this parabola, if you want to think about what it's doing, is a parabola that opens down. It's also been shifted down 4 places, so it's below the x-axis. So it's down here at -4 for your vertex. And we are limited, we are only focused on -3 to 5. So if this is -3, and this is 5, somewhere way over here, so we're only using this one section of our parabola. So our maximum was achieved at the vertex, and our minimum was achieved at this lowest point on our domain of our parabola. All right, so let's try another one. Keep getting more interesting here. Find the absolute max and min values of the following function on the given interval. Then graph the function. Did I graph the function? Oh, I was supposed to graph the function here too. Oh, my bad. All right, so I kind of did it with the other tools, but we can still graph it using these information we have here. You have these 3 points. Graph your absolute max, your absolute min, and your endpoint. So you'd be graphing 1, 2, 3 points, and then you would connect the dots. Nice smooth curve because this is a polynomial, and specifically a parabola. All right, let's find the absolute min and max here. The nice part about our problems is the graphs are multiple choice, so you pick the right one. But you should still have a little bit of a concept of what these functions are doing. Find the absolute max and min of the following graph on a given interval, then graph. So, absolute max and min, start off with your critical points. Where do critical points occur? When the derivative equals 0 or undefined. Now, to take the derivative of this function, we'd probably want to rewrite it. So this is algebra here. Bring your x up so that you can see your power rule. Then take the derivative. So power rule, we multiply, we get +10. X to the 1 less would be -3. If you want to rewrite it, you can. Positive exponents would be helpful because we're actually trying to evaluate this function or find out when it's undefined or 0. So when is this going to be 0? Actually, never. Why? Well, a fraction is 0 when the top is 0. So equal 0 happens when your top is equal to 0. Undefined happens when the bottom of your fraction equals 0. So in this case, it will never equal 0, but the denominator will equal 0 when x equals 0. So this is when it's undefined. So I've broken it down for you. The derivative is 0 when the top is 0. The derivative is undefined when the bottom is 0. So use that trick to help you simplify your work on these problems. So this is our critical point. X equals 0, because that's what makes the bottom 0, which makes it undefined. And then we need to plug in our endpoints. So our endpoints are right up here. So if we plug everything in, we have f of 0, we want to evaluate, f of 0.3, and f of 5. We're looking for the biggest value and the smallest value as our absolute max and min. Plug in 0. Well, that's undefined. Even in the original function. Well, why? You should understand this. We've talked about this before. When your denominator is 0, you're approaching one of two things. A whole, if it can be canceled, which in this case you can't reduce, or a vertical asymptote. So this one you should recognize as being a vertical asymptote here. X equals 0. Now, if you can't, all right, so let's do the other two. So f of 0.3, we plug that in, so -5 over 0.3 squared is equal to, calculator on. So 5 divided by 0.3 squared, so we get -55.56. And if we plug in 5, -5 over 5 squared, well, the 5 reduced, so we get -1 over 5. If I do a decimal so I can compare, we end up with -0.2. Okay, so what have we learned here? Well, let's go back to our definition for, or our rules for finding the absolute max and min, okay? And then we'll talk about this. So if I go back over here, finding the absolute extrema of a continuous function f on a finite closed interval. All right, something that we just found breaks our rules here. Can you see what's causing us to have a problem when it comes to our rules for finding the absolute max and min? We have a vertical asymptote. What does that mean? Well, a vertical asymptote means our function is not continuous. But our question that we need to ask ourselves is, are we on a closed interval that's continuous? It may not be continuous everywhere, but on our closed interval, are we continuous? So if I go back over here, what I need to check, wrong problem, sorry, problem there is, what I need to check is if this vertical asymptote messes me up. Remember, vertical asymptote is a gap in your graph, meaning we're not continuous there. So that's a problem, but only if our closed interval includes that point. So what I forgot to check was if my critical point is actually in my interval. We are only interested in x values from 0.3 to 5. This critical point is not actually in that interval. So this is not in the domain, so we actually don't need to worry about it, which is great because otherwise we would have a problem. We'd have to figure out how to deal with the vertical asymptote. And we are going to learn how to do that. But in this problem, our critical point was outside of our domain, so really we're only interested in the endpoints. So we have a piece of curve that has no min or max in between locally, but we have a min and a maximum value at the endpoints. So that's basically, well, that is what we're dealing with here. So hopefully that helps you. So what I forgot to do, make sure you understand, is once I found my critical point, I forgot to make sure it was in my domain. It's not, so I don't have to worry about it. So focus on the endpoints. We need our absolute max and min. So which of these values is the absolute max and which is the absolute min? All right, so our absolute max is going to be the -0.2, and the absolute min is going to be the -55.56. So if I were to graph this, well, I should probably not draw it like that. I should draw it like this. So x at 0.3 and x at 5. So at 0.3, we are at a seriously negative number way down here. So we'll call this -55.56. This is not drawn to scale. And at x equals 5, we're really close to our x-axis. We're just at a -0.2. And this is a nice smooth curve. Now, how that's connected, we're going to learn how to figure that out a little more detail when we get to concavity. So for now, just connect it with a nice smooth curve. Let's see, which way should this actually be? Well, you can use Desmos to check your work for right now. But this curve, we would be able to determine which kind of curvature, whether it's this way, or a straight line, based on the second derivative. And we're going to get to that in a later section. All right, let's try another one. Find the absolute max and min and the graph. All right. To find the absolute maximum, you start by finding the critical values. This time, hopefully we remember, or critical points, we remember to make sure they're actually in our domain. So the derivative tells us if we have critical points by telling us if the derivative is 0 or undefined. All right, oh boy, we have to find the derivative of this. How are we going to find the derivative of this function? Well, what's happening in between x to the 5th and e to the negative x? Multiplication. So this is a product rule. So let's write it down just for practice. So u and v, remember the product rule is u prime times v plus u times v prime. I'm going to choose u to be x to the 5th and v to be e to the negative x. So u I think we're pretty good on. That's just the power rule. Power comes down and one less. V you might still be trying to figure out and practicing this. So this is a function inside of a function. So this is actually chain rule. So the derivative of e is itself. So e to the negative x. But then we have to multiply by the derivative of the power. And that's the chain rule. The derivative of negative x is negative 1. So we're just multiplying by a negative. So it's negative e to the negative x for the derivative. Plug it in. So f prime of x is equal to 5x to the 4th times e to the negative x plus x to the 5th times negative e to the negative x. All right. Well, we can combine these signs together because they're multiplying. So we have a negative in the middle. Between these two terms, there's actually stuff in common, so we can factor stuff out. X's can come out, specifically x to the 4th, and an e to the negative x can come out. So if I pull that out of the first term, I'd be left with just a 5. Minus, because we're combining these two signs together, we are left with an x, and the e is taken out. In this case, it's very important to do the factoring because we have to analyze this. We have to set it equal to 0 or undefined. Now, undefined requires us to talk about the denominator. So let's rewrite this with positive exponents so that we can see our denominator. So we have x to the 4th times 5 minus x on top. And the e to the x has a negative exponent, so he moves to the bottom. All right, this equals 0 when the top is equal to 0. This derivative is undefined when the bottom equals 0. So we're going to break it up and do the two separate problems. So the top equals 0 when x to the 4th equals 0, or x equals 0. And when the parentheses equal 0. So when x equals 5. The bottom, e to the x, remember we saw that graph earlier. E to the x approaches 0, it approaches the horizontal asymptote, but it never actually reaches 0. That's impossible. So this is never undefined because the denominator never reaches 0. It gets really close, but it never actually gets there. So what we have here, 0 and 5, those are our critical points. I'm going to remember this time to make sure they're in our interval. We're interested in x's from -1 to 6. So this is in our domain, both of them. So we're going to consider both critical points and the endpoints when we go to plug into our function. So f of 0, f of 5, and then our endpoints, -1 and -6. All right, if we plug 0 in, 0 times, well, a number is 0. 5 to the 5th times e to the -5. All right, calculator. Let me write it out first. Make sure you practice the E button on your calculator. So if you have this, my favorite calculator, then the E button, oh, where'd it go, is your ln button. So ln, you're going to have to press the second and then the ln button to get your e to the x. So second e to the x, and then it gives you open parentheses for you to actually put your power in. So our power is a -5. So e to the -5 times 5 raised to the 5. So in case you've forgotten, this little triangle looking thing, that's what creates your exponents for you. All right, so for that one, I got 21.06 if I round. All right, so the next one is -1 to the 5th, e to the -1. So that's going to be e to the +1. And then negative 1 to the 5th is just negative 1, so this is negative e. What is negative e? Well, that's negative 2.71, and it goes on forever, so just round it. And then we have negative 6 to the 5th times e to the negative 6, so e to the positive 6. Okay, that one we need help with. So, going to be negative 6 raised to the 5th. Now, if you don't work out that negative separately, which is how I do it, make sure you put the negative 6 in parentheses, then to the 5th power. If you don't put that negative in the parentheses, you're not actually doing the power on it. You've got to make sure you do the power on it if you're not actually thinking through, is this going to be a negative or a positive? Because it's an odd power, I know it's going to be negative, so I can just do that separately, but just warning you, include the negative in your power. Times e to the 6th power. So write that number down, negative 3137062.298. That's a big number. So I think we know what our absolute min is. So here's our absolute min, because he's such a big negative number. And here's our absolute max. So one critical point actually gave us our absolute max, and one endpoint gave us our absolute min. Now, for this function, this is actually fairly complicated, so I would recommend that you actually take a minute, go to Desmos, and graph this function. So I'm actually going to do that real quick. So, desmos.com. So, our function is y equals x raised to 5th times e raised to the negative x. Make sure I got that right. X to the 5th, e to the negative x. Yes, I did. So here's our graph. And we are limited. Our x values have to be between negative 1 and 6. Negative 1 is less than or equal to how do I do less than or equal? Oh, it'll work. Less than, x is less than 6. Alright, so this is showing us what section we're interested in. So from this point, all the way forever and ever and up. Notice it curves back down, but we are interested in this endpoint here. So that's our endpoint. So our maximum is here. Okay, it's a critical point because it has a horizontal asymptote. Our absolute minimum is this one right here. It's an endpoint because it keeps going lower and lower after that. All right, so that's a graph of that function. We're going to learn more about graphing later too when we'll continue working on it. All right, so those were my examples for absolute min and max. So we're going to talk about more when it comes to the local extrema as we go through this section. So please keep watching your videos, study hard, and I'll see you in the next one.